All right, so last time we talked about the eigenvalue problem, how to set it up, how you end up solving it, and we just did a 2x2 example, which was just a way of showing the algorithm and how you would go forward with other problems. But in this video, I just want to talk a little bit more about special cases when you find some interesting things with your matrices in terms of them being defective versus non-defective. And so we're going to do a couple examples, and to start off, I just want to define a couple terms that are important to know. The first of these is something called algebraic multiplicity. This is sometimes just called multiplicity. And what this refers to is the number of times one specific eigenvalue appears as a root of the characteristic polynomial. And the characteristic polynomial is just denoted p of lambda. So if you don't know what the characteristic polynomial is, we'll get to it in a second. I just want to write this down. And then the second one is called the geometric multiplicity. And so how we define the geometric multiplicity, we know that each eigenvalue lambda has at least one eigenvector that corresponds to it. And so the eigenvectors corresponding to an eigenvalue lambda, these actually form a space. And we call this space the eigenspace, of course. And so what we'll find then as we move forward is that if you do by chance have an eigenvalue that has more than one eigenvector associated with it, then those eigenvectors will be linearly independent. And so what we call the geometric multiplicity then, if we take the dimension, these eigenspaces are capital E's, is what they're denoted. You take the dimension of E for particular lambda, that is defined to be the geometric multiplicity. Okay, so these are just definitions. We'll actually see them in use in a second, but I just wanted to write them down for now. Okay, so let's go ahead and do an example. So this is problem, it's in section 7.2 and it's number 6. And so you're find all eigenvalues and eigenvectors of, and then they give us A is equal to 3, -4, -1, 0, -1, -1, 0, -4, and 2. And it took me so long to find a problem that actually fit what I wanted to do. So this is hopefully going to be a pretty good problem. And so, as we go through, we first, if you remember from last video, we need to find the determinant of A minus lambda I, and we need to set it equal to 0. So our determinant then is going to be 3 minus lambda, -4, -1, 0, -1 minus lambda, -1, and then 0 minus 4, and then 2 minus lambda. And that has to be equal to 0. So what you do is you take this determinant. I won't do it on screen, but you're welcome to do it at home. And what you would end up with is you'd get lambda plus 2 times lambda minus 3 squared is equal to 0. Okay, so this here is the characteristic polynomial. and it's called, like I said, P of lambda. So what we're really doing is we want to find the roots of the characteristic polynomial, and those will be our eigenvalues. So anyway, we have lambda 1 is equal to negative 2, and then lambda 2 is equal to positive 3. But what you'll notice is we have this square, right? So we don't want to just, stop here and say that we only have 2 eigenvalues. We actually have 3 eigenvalues, but 3 is repeated twice. So this has algebraic multiplicity of 2. Okay, because it popped up 2 times in our characteristic polynomial here. This one simply has algebraic multiplicity of 1. But I'm still going to write it down because we'll talk about it, why it's important in a second, is equal to 1. Okay, so that's our characteristic polynomial, and we found our eigenvalues perfectly fine, and our algebraic multiplicities as well. So now part 2, we had to find all the eigenvectors. So to find the eigenvectors, you consider lambda 1 is equal to negative 2 first. So you do, it was sorry, one second. A minus lambda 1 times I, which is equal to A plus 2I, which gives you 5, negative 4, negative 1, 0, 1, negative 1, 0, negative 4, 4. Okay, great. And if you remember back to last video, what we needed to do is we needed to solve A minus lambda 1I times some vector V gives us 0. So what we can do is we can set it up this way like we have been doing. 0, 1, negative 1, 0 minus 4, 4. We multiply it by some vector V, which I call xyz because it's in 3 dimensions. And we should be able to get the 0 vector here. And in the 2x2 case, and even sometimes in the 3x3 case, this was sufficient because you can just pretty much eyeball what x, y, and z is going to be. But as you'll notice in this case, it's going to be a little more tricky to figure out exactly what's going on. So what we have to think about then is what we're actually doing here. So we have a matrix here. We're multiplying it by some vector, and every vector that satisfies this equation gets sent to 0. So if you remember, this is actually just finding the null space of this matrix. A minus lambda 1I. Okay, and how do we find the null space? You form the augmented matrix. 5 minus 4 minus 1, 0, 1 minus 1, 0 minus 4, and 4. Augmented with 0, 0, 0, and now you're free to row reduce. So what we can do is we can just take one step. You'll see these 2 rows here are scalar multiples of each other. So we have 5 minus 4 minus 1, 0, 1, negative 1, and 0, 0, 0. So I don't really care about getting it entirely into row echelon form. I can keep this 5 here because I don't really care about it. I just need to be able to figure out what one vector that works here is. Okay, so the next thing you'll notice is that by the rank nullity theorem, we should only have one vector in our null space, right? So we have pretty much the reduced echelon form of this matrix here, and we know that this has rank 2, and the number of columns is 3. So then by rank nullity, our nullity should be 1, so we should only have one vector that works in this equation here. So what do? We do what we did last time, we just pick a vector. So by inspection, v1, I can make it 0 in the first place, and then 1, 1. No, I can't, sorry, one second. It's actually 1, 1, 1. So I need to be able to get rid of pretty much both this first row and the second row when I multiply it by v. So I just noticed that to get rid of the second row, all I needed to do was make sure that these two entries are equivalent. That gets rid of the second row, but then I still have this 5 up here to deal with. So to get rid of that 5, I needed to include a positive 1 in my first entry of v, and you'll notice that it doesn't affect this term at all because it's 0. So this is something that you'll just have to practice to get pretty good at, but it will come soon, and you'll be able to do this in your head pretty quickly. Okay, so there's our v1, and what we said then, we have this notion of geometric multiplicity, and we said that the eigenvectors corresponding to an eigenvalue form an eigenspace, right? And so here, the eigenspace corresponding to eigenvalue 1 is just going to be the span of this one vector that we found, 1, 1, 1. So what that means then is because 1, 1, 1 is an eigenvector, so is 2, 2, 2, so is pi, 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 and so forth. And the only thing you have to pay attention here is that even though the vector 0, 0, 0 is technically in the span of 1, 1, 1, we don't consider it at all when we're talking about eigenvectors because it's just the trivial solution. So anyway, we have this eigenspace that's spanned by one vector here, so we know the dimension of E1 is equal to 1, so that tells us our geometric multiplicity for this particular eigenvector or eigenvalue is equal to 1. Okay, great. So that takes care of our first eigenvalue, -2. And now we have eigenvalue 2, which is 3. So now we do this. And again, what we need to do is we need to take a minus lambda 2I, which is equivalent to just subtracting 3 times the identity matrix. And that gives us 0, minus 4, 1, minus 1. 0, minus 4, minus 1, 0, minus 4, minus 1. Okay. So what do we do here? We're going to do the same notation that we used up here. So even though you might be able to just look at it and figure out what it is, I'm going to form this augmented matrix here, and we're going to get a better look at it that way. So we have 0, minus 4, minus 1, 0, minus 4, minus 1. There's something on my screen. There we go. 0, minus 4, minus 1, augmented with 0, 0, 0. And now, again, we're free to row reduce. Since all 3 of them are the same, I can keep just one of them. I'm going to make it positive for taste, whatever. And then they're all 0 everywhere else. Okay. So again, here you can use the rank nullity theorem. So you have, I keep doing that. You have 2 rows of zeros here, and you only have 1 non-zero row. So you know that your rank is going to be equal to 2. You know you still have 3 columns to work with. Sorry, your rank is not 2. Your rank is the number of non-zero rows. That was just a stupid mistake. And then that means that your nullity is equal to 2. Okay, so what that tells us then is that we need to be able to find 2 linearly independent vectors that get sent to 0 under this matrix here. So what we want to do then, we can notice first of all that because we have this column of zeros here, it's not going to care what the first value of our vector that we send through is. So I can go ahead and just say that v2 is going to be equal to 1, 0, 0. Because any scalar multiple of 1, 0, 0 will get wiped out by the first column, right? And then the second one, we just do the same way we've done before. It takes a little bit more work, but we can just make it 0, -1, and 4, because that also gets sent to 0. And so you'll notice since v2 and v3 are not scalar multiples of each other, they're linearly independent, which is great. And there's two of them, so we know that E2 then is spanned by 1, 0, 0, and 0, minus 1, 4. Therefore, the dimension of E2 is equal to 2, and the geometric multiplicity is equal to 2 in this case as well. Okay, so we've pretty much finished solving the problem, right? All they asked for was the eigenvalues and the eigenvectors. But I wanted to take it a step further because I want to make a point about why we care about these multiplicities in the first place. So let's go ahead and just tally everything that we know. So lambda 1 had an algebraic multiplicity of 1 and a geometric multiplicity also of 1. And then lambda 2 had an algebraic multiplicity of 2 and a geometric multiplicity of 2 as well. So the reason we care about this is because if we want to be working with a good matrix, then the algebraic multiplicity and the geometric multiplicity should be equal. When I say good matrix, I mean non-defective. So this might be the first time you've heard that term, but in the coming sections, we'll be doing a lot of tricks with diagonal matrices, and we're going to be wanting to work with we're going to be wanting to work with matrices that are non-defective. So there's actually a formula we can use. It's theorem 7.2.11, and it says that n by n matrix is non-defective. So again, a good matrix is non-defective if and only if the geometric multiplicity matches the algebraic multiplicity for each eigenvalue. Okay, so if you want to know exactly why this is true, you can consult the textbook. My job is just to tell you how to work with it and what to look out for. So the question raised then is, okay, is this always the case? Am I always going to find that the algebraic multiplicity equals a geometric multiplicity? And, judging by the theorem I wrote down, the answer is no. And we'll do an example now, actually, where it's not the case. So this is problem, it's in 7.1, actually. It's number 22. And it just says find the, find if A is non-defective. And they say A is equal to 1, 0, 0, 0, 3, 2, 2, negative 2, negative 1. Okay, so how do you, approach a problem like this? Well, you need to go through and you need to find all the eigenvalues and the eigenvectors anyway, because from what you get, you'll be able to determine the algebraic and the geometric multiplicities, and that will tell you if your matrix is defective or not. So you can go through, so to find your characteristic polynomial, I'm just going to give it to you. It's going to be equal to 1 minus lambda, and it's actually cubed. So that tells us that if we set it equal to 0, we have lambda 1 is equal to 1, and it has algebraic multiplicity equal to 3. Multiplicity. Okay, so right off the bat, we know something about this matrix. We know that if we want it to be non-defective, we're going to need to find 3 linearly independent eigenvectors for this eigenvalue lambda 1 is equal to 1. How are we going to do that? We're just going to see if it's even possible. So to find the eigenvalues, you take A minus lambda 1I, which is equal to just A minus I, which is the identity. And you get, this is equal to 0, 0, 0, 0, 2, 2, 2, negative 2, negative 2. All right, so just keeping with notation then, to find the eigenvectors, we're going to put it into an augmented matrix with zeros. And if this is a bit slow, sorry about that, but I want to be very thorough. And then we can row reduce and put it into a form that's better. So I'm going to divide everything by 2, move some rows around, and this is where we're at. Okay, so again, we want to use the rank nullity theorem here. You'll find that since there's 2 non-zero rows, the rank is 2, and is still 3. So it tells us that the nullity is equal to 1. Okay, so then we should only be able to find one vector that works in this particular case here. And one such vector is just going to be equal to 0, 1, negative 1. That should work out fine. Yep. Okay, so then we know that E1 is equal to the span of this vector. And again, we know it's only this vector. We know it can't be more linearly independent vectors because we only have a nullity of 1. And so then the dimension of E1 is equal to 1. So the geometric multiplicity is equal to 1, which is not equal to the algebraic multiplicity, which was equal to 3. So this is a defective matrix. And that's going to make you very sad on exams moving forward if you do come up with one. But what we'll do in the coming sections is we'll teach you how to work with defective matrices, because some are actually more defective than others, and you'll be able to work with them regardless.